Good morning to all. Today we are going to see next point, ion exchange equilibria. For this ion exchange equilibria, in that we are consider the general reaction. Here you can see A plus Br is equal to Ar plus B. Here A plus and B plus are monovalent ion, and the suffix R and suffix R denotes molar concentration of species B or A, and Kab is the selectivity coefficient for ions A, B. We are applying the law of mass action to this reaction. We get here, you can see Kab is equal to concentration of Ar into concentration of B upon concentration of A into concentration of Br. Exchange occur between two ions, different valencies. What I say, exchange occur between two ions of different valency as A and B. We have exchange as like this reaction. Here you can see two different valencies. Using the valencies, we can write the reaction AB plus B A plus R gives AB plus R plus A B A plus. By applying law of mass action for this reaction, we get selectivity coefficient Kab is equal to concentration of Br into concentration of Ba upon concentration of Ab into concentration of Bar, product upon reactant. Kab is equal to product upon reactant. You know the square bracket means it indicates the molar concentration. So selectivity coefficient Kab can be evaluated from experimental data for strongly acidic or strongly basic resin. From this selectivity coefficient, we can evaluate experimental data for strongly acidic or strongly basic resin. And the number of equivalent of exchangeable ions in the resin is equal to total exchange capacity. What I said, the number of equivalent of exchangeable ions in the resin is equal to total exchange capacity. You familiar with the term total exchange capacity, and you had done the experiment breakthrough capacity. In that you calculate equivalent of ions. Next we see for ions of same valency, selectivity coefficient is independent of units used to measure concentration in both the phases. Here you can see in the picture First, KAB is greater than 1. When it is greater than 1, if A has more affinity of resin, if A has more affinity of resin, then selectivity coefficient is greater than 1. Second, KAB is less than 1. When B is held strongly in resin and needs strong external solution as an eluent to accomplish exchange reaction. What I said, B is held strongly in resin. That time KAB is less than 1, and here you can see KAB is equal to 1. That time there is no selectivity for both the ions in the column. What I said, KAB is equal to 1 indicates no selectivity for both the ions present in the column. In this exchange of ion of different valency, KAB, that is selectivity coefficient of this ion, is depends upon the molar concentration. As you see in this here you can see depend upon the molar concentration. The electrolyte which are used, that penetration in resin changes its swelling, and the van der Waals adsorption and variation in the degree of dissociation in the resin phase or external solution is also considerable significance. These other for this system, such influence is totally negligible or absent. Next, now we consider this cationic reaction. Here you can see the cation exchanger equilibria, that is cation, so it is strongly acidic in nature. For this exchange of ions with same and different valency, here you can see the valencies are same, ions are same but having different valencies. Here C minus, here you can see square bracket C minus, it indicates the activity of anion, activity of anion, and suffix R represent the resin phase. Suffix R represent the resin phase. We are just now here this fifth equation divided by this second equation, this sixth equation is dividing by this fifth equation. We get this equation, that is number 7. Here you got the equation contain activity coefficient of, that is Yeah. Activity coefficient. That activity coefficient of ion in the resin as well as in solution form. So we determine selectivity coefficient by considering ratio of activity coefficient of ions in the resin and solution phase. What I said, we determine selectivity coefficient by considering the ratio of activity coefficient of ion in resin and solution phase. And the dilution of external solution has no effect on equilibrium. You familiar with term equilibrium? The relative amount of ion in resin phase is marginally charged. KAB changes if AR or BR like this. Next point is inorganic ion exchanger. Inorganic ion exchanger. Here in inorganic ion exchanger, 4 points are there: hydrous oxide, salt of multivalent metal. Third one, salt of heteropoly acid, and last one is synthetic ion exchanger. First, hydrous oxide. They are anion exchanger. Behave like an anion exchanger. Hydrous oxide, oxide of chromium, zirconium, tin, and thorium behave like an ion exchanger. They are like polymer cross linked by oxygen bond between metal atom. They are like polymer cross linked by oxygen bond between metal atom, and it is anion exchanger. So OH minus group is hydrolyzed in acid media and they behave like a anion exchanger. And next one is at the low pH, they show better exchange capacity. Example, zirconium dioxide. At low pH, they show better exchange capacity. So behave as a cation and anion exchanger in pH resin region of pH range 5.8. Next, hydrated AlO3 has anion exchanger property and has exchange in property, ion property. Next one is salt of multivalent method. Here it is a cation exchanger. Hydrous oxide is anion exchanger. Here salt of multivalent metal is a cation exchanger. In that example is hydrous phosphate oxide behave as a cation exchanger, and the property depend upon the method of preparation of zirconium phosphate. Here high temperature improves selectivity coefficient during salt. In hydrous oxide we show the low pH show better exchange capacity, and here high temperature improve selectivity coefficient on during salt. During salt increases exchange capacity and separation of ion by this material is accelerated by ratio of high selectivity coefficient. Apart Apart from this, zirconium, salt of titanium, the second arsenate, molybdate, tungstate can replace phosphate, give new exchanger. Third one is salt of heteropoly acid. Here you can see in the salt of heteropoly acid, it is a cation exchanger. And here you see the example. It behave like cation exchanger. Such property depend upon ability of different cation. Last one is synthetic ion exchanger. It is inorganic, and here you can use inorganic and organic resin. In that, organic resin are polymeric resin matrix, and next one is the resin composed of polystyrene and divinyl benzene. Resin composed of polystyrene and divinyl benzene. In polystyrene, sites for exchangeable functional group, and in divinyl benzene, cross-linking agent offers stability. So thank you.